So in this lecture, we're going to discuss the conservation of probability in quantum mechanics. So recall the Born interpretation of the wave function psi, which is a function of space and time. And that what it said was that suppose that we want to find the probability of a small volume, say dV, around the space point r, where the space point r, the xyz coordinates are given by this. Then the probability that we find the particle in that little volume is given by the probability density at that point times the little volume. So if you write it more explicitly, it's going to be rho, which is the probability density, is nothing but psi star So this is the probability of finding the particle in a small volume at the point where this is the point r. But remember that psi, the wave function, is also a function of time. And so there is some dynamics of psi which is governed by the Schrodinger equation. And that means that the probability density, rho, is not going to be a static function, that it is going to depend on time as well as space. So in this lecture, we're going to find out how rho depends on time. So before we do that, let me remind you some results, relevant results that we derived before. So in one of the previous lectures, we showed that suppose we had the wave function and we normalized it, and let's call the normalization n, and the normalization was the integral over all space of the probability density dV. So if this looks unfamiliar, let me write it out in more detail. So this is an integral over all space, so these integrals go from minus infinity to plus infinity, and then rho is nothing but psi star of r, and there's dependent on t, and then this is going to be d of x, d cubed of x, which is the volume element. And in a previous lecture, we showed that the Schrodinger equation implies that the normalization of the wave function, once we fix it, doesn't change with time. So this is 0. But what does this mean? This means that the total probability is going to be a conserved quantity. That if we want to find the particle will be somewhere in space. That means that this integral has some finite value, and that probability is not going to change. Suddenly the particle is not going to escape from our space, and therefore the probability, the normalization is not going to change. So in this lecture, we're going to find a related result, which is kind of the local version of this result. So we're going to assume that we have normalized our wave function, that is n, the normalization is 1. If it's not normalized, if our wave function is not normalized, we can always introduce a normalized wave function by dividing the unnormalized wave function by square root of n, as long as the wave function is normalizable. So now we want to find out how the probability density changes as a function of space and time. So let's start with the Schrodinger equation. So we have I h bar d psi by dt is equal to minus h squared by 2m, and now we're in 3 dimensions, so this is Laplacian times psi plus some potential function times psi. So let's call this equation number 1. And now what we're going to do is that we're going to take the complex conjugate of this, the complex conjugate. So that's going to give us I h bar d psi star by dt is equal to minus h squared by 2m, the Laplacian, and then we have psi star plus v. Now we are assuming v to be a real function, so this is going to just remain v, and then we have psi star. So let's call this equation equation 2. And now what we are going to do is that we are going to multiply equation 1 from the left by psi star, and then we are going to subtract from that equation 2 after multiplying it with psi from the right. So if we do that, what do we get? We get on the left hand side I h bar, and then we get in brackets psi star del psi by del t, and then this minus sign becomes plus sign because of this, and so we get plus del of psi star by del t times psi. Let me not use the dot for times because we're going to use the dot for something else. So on the right hand side, let's look at this term at first. So this term is going to have psi star multiplying it, and this term is going to have psi multiplying it. So when I subtract these two equations, these two terms will cancel out. So what we'll have is that these two terms left. So what do they give me? They give me minus h bar squared by 2m, and then let me start a square bracket, and then inside the square bracket I get psi star, the Laplacian psi, and then I have minus the Laplacian psi star times psi. Okay, let me put this in bracket to make sure that we are not applying the Laplacian operator on this guy. So this is our result. Now let us simplify it somewhat. So we have h bar on both sides, so we only need to keep 1. And then on the left hand side, what we can do is that we can multiply it divided by I. So on the left hand side we have del by del t psi star of psi, right? We can write these two terms as one term. And on the right hand side I have minus h divided by 2i m, because I've divided both sides by I. And here the first term I can write it as the gradient operator, the divergence operator, sorry, acting on psi star gradient of psi, and then minus we have the gradient of psi star dotted with the gradient of psi. So what I'm doing is that if I expand this out, I get two terms. One is this guy acting on this, another one is this guy acting on this. So this guy acting on this is this term, the other term is here, and I'm writing it with a minus sign. So this is just using the Leibniz rule. And from the second term, we get minus the divergence operator times the gradient of psi star, let me put this in another bracket, times psi. So this is my first term, and then I'm going to have another term which is going to come with a plus sign, and the term is going to be gradient of psi star dotted with the gradient of psi. So we have four terms on the right hand side, but we see that this term and this term, they're the same, and they come with a minus sign, with a relative minus sign, so they cancel each other out. So on the left side we get d by dt, but this thing is nothing but the probability density, rho. And on the right side I get minus h bar by 2im, and then I can factor out the divergence operator, and inside I have the term, a vector, the vector is psi star gradient of psi minus the gradient of psi star times psi. So this is a vector, and the divergence of the vector makes it a scalar. So we can write this as divergence minus times a vector s. What is the vector s? The vector s is going to be h bar by 2im, and then this thing, psi star gradient of psi minus psi gradient of psi star. But this thing, the first factor term is just the complex conjugate of this thing, and there's a minus sign. So this is some complex number minus its conjugate. And we know that that's going to give us h by 2im times 2 times I, the imaginary of this guy. And therefore, this 2i and 2i will cancel out, and then we have left over h bar by m times the imaginary of psi star gradient of psi. And on the left hand side I have this is the definition of S. So we can write this equation now using this definition of S as d rho by dt, and then we can take this thing on the right side to the left side, and then we will have plus the divergence of S is equal to 0. So this is the equation that I was after. So what we know is that rho has a particular meaning. Rho is the probability density, and then S has the interpretation of probability current density. So what do I mean by this? What I mean is this. Remember the meaning of the divergence. What divergence means is that suppose you have some small volume and there is some fluid flowing through this volume. So there's some fluid flowing through this volume, or something is going through this volume. But suppose that the amount that is going in is not the amount that is coming out. So this happens, for example, in electromagnetism when we have a charge inside a Gaussian surface. In that case, we have electric field going out, and in that case, the flux is non-zero. So the divergence of S, what it's telling me is that what is the net amount of S, the current S flowing out of a small volume, if there's a net flow out of it. If there is, that means that the probability that is stored in that region is going to change with time. And that's basically, so this equation it's a general equation. It crops up in many branches of physics, and it's called the equation of continuity. Okay, so this is the probability density, and this is the S is the probability current density. It's not the probability current, it's the density. So it is the amount of current that flows through some surface area. So where else do we get probability current? Where else do we get the equation of continuity cropping up? We get it in charge conservation. In electric charge, if there's some electric charge over here, say, and some of this electric charge is flowing out, then we have a current. And so the charge density in this place is going to decrease, and that decrease is going to be given by how much current is flowing out, the net current that is flowing out, which is given by divergence. So here we can think of, in quantum mechanics, the probability as a kind of an incompressible fluid, so that the amount of fluid that is contained in some small region changes with time if some probability leaks out. So this is a first order differential equation. So let's see how what this equation implies globally. So what we can do is that we can say, okay, suppose we have some system which has some volume V, and so what we want to do is that we want to integrate that equation over that volume. So we have d over dt, and we are integrating it over some volume dv, and let's call this region, the volume, to be sigma, and then its boundary is denoted by del sigma. So we are integrating this over the whole volume, and then plus this is going to be equal to the integral over the whole volume of the divergence, the divergence of S dV is equal to 0. Now, on the left-hand side, we can write, so the first term on the left-hand side, we can write it as d by dt times d rho, rho dv, right? Because this thing is, we have integrated over the volume, so it doesn't depend on space coordinates, but it can only depend time coordinates. So taking its derivative is the same thing as taking its partial derivative, and then we can just once we have converted this to a partial derivative, we can do the derivative under the integral sign, and we get this thing. But what happens to the second term? The second term, we can simplify this into a term which is an integral, a surface integral over the surface surrounding that volume, and the integrand will be S dotted with the area equals to 0. So to come from here to here, we are using Gauss's divergence theorem. If you don't know what Gauss's divergence theorem is, it goes something like this. Suppose you have some volume V, and it's surrounded by some boundary surface called del V, then the divergence of some vector V, so let's not call it V, let's call it something else, say J, integrated over that whole volume is equal to the vector dotted with the surface, so this is a volume integral and this is a surface integral. So what is dA? dA is just the area element vector we have. Okay? So using this, we can convert our differential equation into an integral equation. And now what is this thing? What is the left-hand side? The left-hand side is the normal. So, okay. Now let's see what happens if I let my V, my system, to be the whole universe. So I let V to the volume. It's a confusing note. I'm confusing you with my notation. I'm letting this thing to be the whole universe. So what happens is that then this guy is just the normalization. So on the left, the first term is going to be d by dt times n. And the second term, what will it be? It'll be the probability current through some surface at the boundary of space. But of course, we are assuming that the particles all remain in finite part of our space-time. And therefore, what will happen is that when we go to infinity, psi star and psi and its gradient, they're going to vanish. So at the boundary of space, the current S is 0, meaning that no particle is actually flowing out of space outside our universe. And if we do this, if we assume that, then of course, in that case, this thing is going to be 0. And therefore, we are going to end up with this 0. And this is dN by dt is 0, which is exactly the result we had derived earlier about the normalization of the wave function being a constant of time. Okay, anyway, just to recap, what we've done in this lecture is to provide you with a local version of the conservation of probability.